So we have seen two approaches to deal with the deadlock problems. One of the approach that we have discussed is the deadlock prevention, and the second approach that we have discussed is the deadlock avoidance. And we have said that there is a third approach in which the deadlock can be managed, that is the deadlock detection and recovery. So in the third approach, we will discuss about detection. That means the system will check if there is a deadlock in the system. If there is a deadlock, then the system will try to recover from the deadlock. So we have deadlock detection and recovery approach. Now to check whether there has been a deadlock in the system or not, the algorithm that is followed is similar to the safety algorithm of the Banker's algorithm. Okay. So again, in this case, we will use a number of data structures. The data structures are, the first data structure will be available, as in case of Banker's algorithm, and available will be of dimension m, because we are assuming that there are m number of resource types in the system. The second data structure will be allocation, which is a matrix of dimension n by m when there are n number of resources in the system and there are m number of resource types. Okay. And the third data structure, which earlier we have said that every process, the ith process, puts a request vector request I, which is of dimension m. We can also consider this to be a matrix. So if all the processes wants to put some request simultaneously, then all the request vectors taken together becomes a matrix. So we have a request matrix which is again of dimension n by m. Okay. So in both the cases, whether it is allocation matrix or request matrix, a row in the allocation matrix will indicate the numbers of different resource types which are allocated to process Pi. Similarly, the request matrix, the ith row in the request matrix will indicate the number of instances of different resources which are requested by process Pi. Okay. So with these data structures, we can write the deadlock detection algorithm like this. So the algorithm will be of this form. Again, here we assume that there are two data structures. One data structure is work, which is again of dimension m, and this work is initialized to value available. Okay. And there is a second data structure, a Boolean vector finish of dimension n. In our earlier case, we have assumed that initially every element of this vector finish is set to false. In this case, we will assume that finish I will be equal to false if request I is equal to 0. When I say request I equal to 0, request being a vector, this indicates that every component of request vector is 0. Okay. So effectively that means that the process Pi has not put any request for any resources. Okay. And finish I will be equal to true sorry, the finish I will be equal to false if allocation I is not equal to 0. Okay. That means if there is some resources which are allocated to process Pi, in that case finish I will be equal to false. Okay. And finish I will be equal to true if allocation I is equal to 0. That indicates that the ith process is holding some of the resources. So our assumption is, since we are trying for detecting whether there has been a deadlock in the system or not, our assumption is that a process which is not holding any resource, that is not responsible for the deadlock. A process which is holding some resources, that is allocation I is not equal to 0, that is a process which may be responsible for occurrence of the deadlock in the system. So for that we set finish I equal to false. Okay. In the second step, what we do is you find an I. So you find that this part of the algorithm will be similar to deadlock safety algorithm. So you find an I such that finish I is equal to false and request I, that is the request vector put by this ith process, is less than or equal to work. That means whatever the request the process Pi has put, that can be met with the help of available number of resources. Okay. If no such I, then go to step 4. Okay. If there is such an I for which finish I equal to false and request I is less than or equal to work, what we do is we assume that the process Pi will be able to complete its execution with the help of these requested resources. Okay, here we take an optimistic assumption that the process will not put any further request in future. That may not be true. So even if the process puts further request, if there is any deadlock because of that new request, that will be detected later. Okay, so at least for the time being, because this condition is true that request I is less than or equal to work, so at least at present, this process is not responsible for occurrence of the deadlock. Okay, so that is our optimistic assumption. So in that case, what we do is we modify the work vector by work plus allocation I, because if the process is complete, it will release all the resources which are allocated to it. Okay, and then we set obviously finish I equal to true. Okay, then go to step 2. Okay, then in the fourth step, we are coming to fourth step from the second step. In the fourth step, if we find that there is some I for which finish I equal to false, then we say that there is a deadlock. But here if we find that for all I finish I equal to true, that means the system is not in deadlock. Okay, so if we find that if finish I equal to false, for some I, okay, obviously I has to be greater than or equal to 1, but less than or equal to n, where n is the number of processes. Okay, so if we find that finish I equal to false for some I, then the system is in deadlock. Okay, and we can also identify the processes which are in deadlock, because it will be the processes for which finish I equal to false. Okay, so you find that following this algorithm, which is similar to banker safety algorithm, we can detect whether the system is in deadlock or not. Then in the recovery part, what you have to do is, once you detect that there has been a deadlock, then obviously if the process goes to deadlock, some of the processes has to be killed so that the system comes out of the deadlock. Okay. So there the question comes that what are the processes that you should select for to be terminated? Okay, so there are different criteria that can be used. One criteria can be a process which has executed for minimum amount of time. We can kill that process, of course, without knowing that what is the future time requirement of the process. Okay. The other criteria can be a process which is holding minimum number of resources that can be killed, because in that case the cost of killing will be minimum. If you kill a process which is holding maximum number of resources, then if the process, when that process is restarted, it has to regain all those resources. That means cost involved will be more. So different approaches or different criteria can be used for selecting a process which is to be terminated, or which is called a victim process. Okay. Now if you analyze this deadlock detection algorithm, or even the Banker's algorithm for deadlock avoidance, you will find that the time complexity of both these algorithms is order m into n square. Is it not? Because if there are n number of processes, and in this step 2 that find an I such that these conditions are true, this itself will take n square amount of time. Okay, and because there are m number of resource types, that means every vector available, request, all these vectors are of dimension m, so total execution time complexity will be of order m into n square. Okay. However, if in a system we have single instances of every resource type, maybe we have got m number of resource types, but every resource type is having single instance of resource. Even then, the time complexity will be of order m into n square. Okay, but we can, in such specialized situation where every resource type contains only a single instance of resource, we can have another kind of algorithm, that is a graphical algorithm, where the time complexity can be reduced. Okay, so there what we will do is, in case of deadlock avoidance, because we have said that in case of deadlock avoidance, every process has to declare in advance what is its maximum requirement. Okay, so here also we assume that every process in advance, when it declares its maximum requirement, then we will form a claim edge in the resource allocation graph. We have already discussed about resource allocation graph. Okay, a resource allocation graph is a directed graph where whenever a process puts request for a particular resource type, you just make a request edge from the process node to the resource node. When the resource is allocated, you convert that request edge to an allocation edge which starts from the resource node, terminates on the process node. For deadlock avoidance, in addition to those request edge and allocation edge, we introduce another kind of edge, because every process will declare in advance its maximum requirement. So what we put is, we form the claim edges from every process to the maximum resources that are needed. Okay, and those claim edges are to be formed before the process starts execution. Right? So once you form those claim edges, a claim edge will be converted to a request edge when the process actually puts request for that particular resource. Okay, and the rest of the things is similar. The request edge will be converted to an allocation edge when the resource is actually allocated to the process. Okay, but the next part is also different. When the resource is released by the process, in our resource allocation graph we have deleted the edge. In this variance of the resource allocation graph, what we will do is, we will convert the allocation edge to claim edge again. The reason being, we are not sure when a process has released the resource, whether that same resource will be requested again. That is not known, because the process simply said that these are the maximum number of resources that is needed. But how long and in what sequence, that is not known. Maybe a process has released the resource, but later on it will need it again. So instead of deleting the age, you convert the allocation age to claim age whenever the process releases the resource. Okay. Now within this type of graph, as we said, that this algorithm will be applicable only when every resource type contains a single instance. And we have seen earlier that when the resource types contain single instances, in that case, presence of a cycle in the graph means there is deadlock. So here also, once we make such a type of graphical representation of the resources and the processes, the request nature, all these things, then the problem is to determine whether there is a cycle in the graph or not. And for detection of a cycle in the graph requires a time of order n square, where n is the number of processes. Okay, so you find, and this cycle detection is required for both for deadlock avoidance as well as for deadlock detection, right? So in both the cases, the time complexity will be of order n square, whereas if we follow the usual Banker's algorithm, the time complexity will be of order m into n square. So you find that we get a reduction by an order 1, and this is applicable both for the deadlock avoidance as well as for deadlock detection. Okay, so we can have a reduced complexity. Okay. Now all these deadlock problems that we have considered, those are concerned with the resources and processes which exist in a particular system. Okay. But how do you deal with deadlock problems in a distributed system? So let us consider the next problem, that is deadlock in distributed environment. In distributed environment, the deadlock problem is much more complicated, because here the processes and the resources are not in the same machine. The processes are distributed in different machines. The resources are also distributed in different machines. It is possible that a process in one machine requests for a resource which is available in another machine. Okay. So, and you find that in case of deadlock avoidance, though it is the ideal solution, we have seen that in case of deadlock avoidance, every process has to declare in advance that what is its maximum requirement, and that is that is an information which is very difficult to get. Okay, because in most of the cases, it is not possible to tell in advance that what is the maximum requirement. The requirement may be generated dynamically. Okay, so though deadlock avoidance should have been the ideal solution, but in practical cases, this is very difficult to implement. But what can be implemented is the deadlock detection and recovery, but at the cost of execution time. But that is a practicable solution. And the problem is much more complicated in case of a distributed environment, because on different machines I have different processes which are of varied nature. Okay, so in case of distributed environment, people don't try to implement a deadlock avoidance algorithm. Rather, what is tried is either deadlock prevention or deadlock detection and recovery. Okay, so let us now discuss about the deadlock recovery, detection and recovery in case of distributed environment. So we'll talk about deadlock detection and recovery. So here, as we said, that the processes are distributed in different machines, the resources are also distributed in different machines. Every machine knows its own resource and its own process, but it may not know what are the resources, and the resources may be known, but it may not know what are the processes which are running in other machines. So the approach that will be followed is every machine will maintain its own resource graph. Okay, because the machine knows that what are the processes which are running in the machine, the resources which are available in the machine. So every machine can maintain its own resource graph. But because we are discussing about the deadlock in distributed environment, the global picture is also necessary. So we assume there is one machine which is the central coordinator, and it will be the responsibility of the central coordinator to maintain the resource graph of the entire system. Okay. So every machine in the network in distributed environment has the responsibility of transferring the information about the resource graph to the central coordinator, so that the central coordinator can maintain the global resource graph. Okay. So that can be done in one of the two ways. You will have a change in the global graph only when there is a change in one of the local graphs. Okay. So whenever some changes occur in a local graph by means of either adding a new edge or deleting some existing edge, or some process quits, okay, in that case, whenever there is some change in a local graph, that change is communicated to the central coordinator by the corresponding machine, and the central coordinator can modify its global graph accordingly. Okay, so that is the first approach. That is, whenever there is change in any of the local graphs, the corresponding machine will communicate the change to the central coordinator. The second approach can be that instead of transmitting the message on every change, the machines can send the message to the central coordinator periodically. Okay. So whenever the message is sent, it just sends that whatever updation has been made in the local graph since the previous updation was communicated. Okay. So maybe during this time, say 5 edges have been deleted, or 3 new edges have been added. Okay. So this updation information will be sent to the central coordinator periodically by every machine, and accordingly the central coordinator will modify the global resource graph. Okay. Then this deadlock detection has to be done by the central coordinator. And central coordinator, if it finds that the system has gone into deadlock, when I say system, it includes all the machines in the network, in the distributed environment. So when the when the central coordinator finds that the system has gone into deadlock, it will decide to kill one or more processes so that the system comes out of the deadlock. Okay. So you can have a system like this. Suppose in a particular machine, in a particular system, we have 2 machines. So we have machine 0 and we have another machine, machine 1. Okay. In machine 0, suppose we have 2 processes running, process A and process B, and at a particular instant of time there are, say, 2 resources, resource S and say resource R. Okay. So at a particular instant, maybe resource S is allocated to process A. A has put a request for resource R, and R is currently allocated to resource B. So this is the resource allocation graph in machine 0. Similarly, in machine 1, the situation may be something like this. Suppose in machine 1, there is a single process C, and this process C has put a request for the resource S. And you find that the resource S is not in machine 1, but the resource S is available in machine 0. Okay. And there is another resource set T. So during this period, during the same time, maybe resource T is allocated to process C, and C has put a request for resource S. So this is the resource allocation graph in machine 0, and this is the resource allocation graph in machine 1. Okay. With this, two local resource allocation graphs, the global resource allocation graph will look like this. We have processes A, we have process B, and we have another process C. Okay. The resources are S, R, and T. Okay. And the edges will be T is allocated to process C, C is requesting for resource S, S is allocated to process A has put a request for resource R is allocated to process B. So this is the global resource graph, and this global resource graph is maintained by the central coordinator. Okay. And you find that the central coordinator finds that there is no deadlock in the system because there is no cycle. Okay. Now in this situation, let us assume that we have a situation that B has released resource R. B releases resource R, and after releasing resource R, the B has put a request for resource type T. Okay. Now when B releases resource R, that means this edge has to be deleted. So machine 0, because this is a local resource graph of machine 0, the machine 0 sends an information to the central coordinator that the edge from resource R to B is to be deleted. Okay. B, after deletion of this, puts a request for resource type T. But T is currently allocated to C. So there has to be a request edge generated from process B to resource type T. And B is in machine 0, resource type T is in machine 1. So this machine 0 has to send the corresponding request to machine number 1. Okay. And machine number 1 now sends this message that a request S has been generated from process B to T to the central coordinator. Okay. So I have two machines, machine 0 and machine 1. Machine 1 sends the message that edge RB has been deleted, and machine 1 sends a message, updation message to the central coordinator that a request is BT has been generated. And these two are two independent messages. Okay. The central coordinator will get the message after some delay, right? So if it so happens that the message from machine number 1 reaches the central coordinator before message from machine number 0. Okay. That is a possible situation. That message from machine number 1 regarding generation of a request S from B to D reaches the central coordinator before the message from machine 0, that deletion of A's from R to B, reaches the central coordinator. Okay. So in such case, while updation of the global resource allocation graph, what the central coordinator will do? The central coordinator will make, because it has got the message from machine number 1 first, so it will simply make a claim edge from B to T, a request edge from B to T. And now the central coordinator finds that there is a cycle. So since the central coordinator finds that there is a cycle, so it will assume that there has been a deadlock and one of the processes will be killed unnecessarily. Okay, and this is a situation which is called false deadlock. Okay, so naturally we don't want this false deadlock to occur in a system. So you have to think of that how to avoid this false deadlock. Okay, so to avoid this false deadlock, the approach that is taken is you maintain a global clock. So every machine in this distributed environment will have a global clock. Whenever a message is sent from any of the machines to the central coordinator, the message will be sent along with the timestamp, and the timestamp is generated by the global clock. Okay. So what the central coordinator can do is, once the central coordinator gets this message from machine number 1, now you find the sequence. We have said that first in machine number 0, process B releases resource R. Okay. That means the first message that is generated is that edge RB has been deleted. So that is the first message. RB, this edge deleted. After deletion of this edge, process B puts a request for T. Okay. So the second one will be that edge BT inserted. Okay, so this is an updation information that will be generated first by machine number 0. This updation information will be generated next by machine number 1. Okay, so if there is a global time, a global clock, then the timestamp of this RB will obviously be less than the timestamp of BT, because this is generated later. So it will have a higher timestamp than this one. Okay. So what modification can be done is, whenever a message, updation message, is transmitted to the central coordinator, the message is always accompanied with the timestamp. Okay. The central coordinator, once it gets a message which can lead to a deadlock like this, because this is the adverse situation which we don't want to occur. So whenever the central coordinator gets a message which can lead to a deadlock, the message has come along with the timestamp, immediately the central coordinator will broadcast a special message to all the machines in this distributed environment, informing that, look, this is a message I have got with this timestamp which is going to lead to a deadlock. Okay. So if you have any message earlier than this, please transmit. Okay. So on getting this special request from the central coordinator, all the machines will immediately transmit any message they have earlier than this timestamp to the central coordinator. Okay. So at this time, this machine number 0 will also transmit this information to the central coordinator, whose timestamp is lower than the timestamp of this. Okay. So once this message comes to the central coordinator, now the central coordinator will find that this is RB does not exist anymore. Okay. So because this edge does not exist anymore, so there is no cycle and there is no deadlock. So we can avoid the problem of such false deadlock by making use of the timestamp mechanism, or the timestamp is controlled by a global timing. Okay, and you find that here we have tried to determine the deadlock by a central coordinator. It is the central coordinator which is finding out whether there is a deadlock or not. So this type of approach is called centralized deadlock detection approach. Okay, because the deadlock is being detected by the central coordinator. We can have the second approach for detection of deadlock, which is called a distributed deadlock detection. Okay. Central coordinator? Not the central coordinator is a machine. A process can be a deadlock.
It's also detecting the sometimes the resources. So I mean,
no, what are the resources that it wants to have? Only the data structure. The process in the central coordinator, see, what is the central coordinator? Central coordinator is a process running on a particular machine. That machine can have other processes in addition to the central coordinator. Okay, those processes can be in deadlock. But the process which is detecting deadlock, this is not in deadlock. Okay, so
when it wants to interact with other machines in this system, it wants input-output process, and so it will require the input-output resources. So
okay, for those cases, some special priority can be given to this coordinator. So whenever this central coordinator wants to get some resource, the resource has to be preempted. Something like can be done.
and what will happen if actually the B is not being freed by resource R? B doesn't free resource R.
Then this is in deadlock.
Then how it is?
Then there is actual deadlock.
Then how it's?
The central coordinator determines that there is a deadlock. It will select one of these three processes to be terminated, following one of the criteria. As we said, that a criteria can be, one of the criteria can be a process which has been executed for maximum amount of time. That will be retained. A process which has been executed for minimum amount of time, that will be terminated. That is one criteria. So some such criteria can be used by the central coordinator to kill a process. And if you kill any of these three processes, the system will come out of deadlock. Okay. So in case of distributed deadlock detection mechanism, every machine in the system or every process in every machine in the system takes part in finding out deadlock. Okay. So here what we'll do, let us assume that we have got three machines. So we have machine number 0, machine number 1, and say machine number 2. Okay. Now in machine number 0, let us assume that there are three processes. Process 0, process 1, process 2. Here again we can have 3 processes, say process 3, process 4, process 5. Okay. Here again we have 3 processes, process 6, process 7, maybe say process 8, and process 9. So let us assume that there are 4 processes in this system. Okay. Now at a particular instant of time, we can have a situation like, I am not showing the resource nodes. Okay. So a graph that we'll be using here is again a variant of the resource allocation graph, where whenever a process Pi puts a request for resource Rj being allocated to process Pj, it is as if that process Pi is waiting for process Pj to do some operation. So I can simply eliminate the resource node from the graph. And the type of graph that we get is called an wait for graph. Process Pi is waiting for process Pj to release resource Rj. Okay. So we can simply eliminate the resource node Rj from the graph and make a directed edge from Pi to Pj. Okay. So that is the kind of graph that we'll be using here. So at a particular instant of time, we can have a situation like this, that process 0 is waiting for process 1 is waiting for process 2, and all these are in the same machine. Process 2 may be waiting for process 3, where process 3 is in machine number 1. Process 3 may be waiting for both process 4 and process 5. Maybe process 5 is waiting for process 7, process 7 is waiting for process 9, process 4 is waiting for process 6, process 6 is waiting for process 8, and process 8 is waiting for process 0. I can have a situation like this. So if you analyze this graph, you will find that this part of the graph does not lead to deadlock, whereas this part of the graph leads to a deadlock. Okay. Now, how to detect this deadlock in this distributed environment? One is centralized approach that we have already said, that the central coordinator will maintain this entire graph, whereas individual machines will maintain this part of the graph. M0 will maintain this part of the graph, M1 will maintain this part of the graph, M2 will maintain this part of the graph. Okay. But in this case, we don't have any central coordinator. We have all these individual machines, and every machine will, or every process will take part in deadlock direction. Okay. How to do it, we'll see in the next class.